the pieces of our work from my dissertation that I think you all might find the most useful. So with that, I think probably most of you are very familiar with the map on the right, but for the uninitiated, I'll just briefly say that in 2014, the EPA came out with their final plan to clean up the contaminated bed sediment in the Duwamish Superfund site. And it involves actively remediating, which is just to say dredging and capping a little bit under half of the contaminated area and allowing a little over half to naturally recover, which they call monitored natural recovery. And basically the idea there is to allow cleaner sediment from upstream to bury areas where bed sediment erosion is minimal. The goal of my dissertation was to understand the hydrodynamics, particularly of the salt wedge intruding from Elliott Bay in Puget Sound, and then to try to understand the impact of salt wedge dynamics on sediment transport. And in order to understand what was happening to sediment in the estuary, I needed to understand when and how much sediment was being delivered from upstream. And so I took a look at the upstream loading data that was available. And then that upstream loading analysis, I think, is going to be probably the most interesting part of this to all of you. So that's what I'll mostly focus on. But I'll also briefly overview what my measurements show about the life cycle of sediment in the estuary. And I'll also try to sneak in a little bit of the hydrodynamics where I can, because they're pretty darn neat. So before I dive into the data, I want to take a second to talk about how we estimate suspended sediment loads in general. Understanding suspended sediment loads is really important for planning and managing rivers, estuaries, and nearby coastlines. And historically, measuring the total amount of suspended sediment being carried by a river at one point was pretty challenging. Nowadays, technological advances have made the measurement much easier, but maintaining the sensors for continuous measurements is actually still pretty expensive. And so as a result, it's really common to have, hypothetically, say an 85-year record of continuous daily river discharge measurements with, say, only a fraction of that amount of sediment loading measurements, taken sporadically and with a bunch of gaps in between. And so the question is, how can we estimate past loads and future loads from sparse data like this? And the answer is that you try to develop a statistical relationship between river discharge and the sediment loads. Suspended sediment loads tend to vary non-linearly with river discharge, which means that if you plot the log of both, you tend to wind up with them falling roughly on a straight line. And if you perform a statistical regression, the result of that is what we call a rating curve. And once you sort of determine the coefficients that govern that line, you can then plug in river discharge to that relationship and get past scenario estimates and future scenario estimates of suspended sediment load. So it's basically a tool that you can use. And it's important to emphasize here that rating curves provide best guess estimates of sediment loads. There's a lot of scatter that you tend to see in the data points around the rating curve. This is a hypothetical imaginary one, but it's pretty representative of what you tend to see in real life. And since this is plotted in log space, even small distances from the line actually represents a pretty big absolute amount. And so the sediment rating curve is providing you with an estimate, but not the absolute answer. In addition to which, sediment transport is a notoriously thorny subject that depends on nonlinear interactions between sediment supply, weather patterns, hydrology, and watershed management. But given that usually the available sediment load data isn't continuous and is typically pretty sparse, this rating curve approach is really typical and is very widely used. So what data is available for the Duwamish? There are actually 3 data sets from the USGS. The first was from 1963 to 1966 at Tukwila, where they did daily measurements and estimated the load from a single vertical measurement in the center of the channel. The second effort was from 1996 to 1997, also at Tukwila, but a little bit further seaward. Sampling for that effort was roughly monthly, but sometimes more frequent if there was a storm that they were trying to capture. The sampling method used in the 90s was an isokinetic measurement that was both depth and width integrated. Finally, the USGS did some more recent sampling beginning in 2013 that I believe is still ongoing. And these measurements are continuous 15-minute turbidity measurements that have been calibrated to suspended sediment concentration using large volume, isokinetic, depth, and flow integrated methods with replicate samples. So basically, this most recent data set in pink is like the gold standard of sediment load measurements. Now, a couple of things about these three data sets. The 60s and 90s data, which is the gray and the blue, they were used in the past with flows from the Auburn gauging station, but I'm plotting them here against Tukwila for two reasons. First, to better be able to compare them to the 2010s data, and second, because the ultimate goal here is to estimate the loads into the estuary, and flows at Tukwila can be up to 10% greater than those at Auburn. The 2010s data I've detited and daily averaged so that this plot with all three data sets on the right here is as apples to apples a comparison as possible. With that said, there seems to be a pretty clear trend toward decreasing loads since the 60s. And there are some perfectly valid physical reasons why this might be the case. The Howard Hansen Dam was finished in 1962, and dams generally tend to reduce sediment loads downstream. There have certainly been plenty of land use changes throughout the watershed since the 60s, and there was a shoreline stabilization effort in the green that may have contributed to decreasing sediment loads. But you can't completely discount the fact that these three data sets use different sampling methods. The single center of the channel method used in the 60s may have overestimated the total amount of suspended sediment in the cross-section. It's a little bit hard to imagine that this could cause a nearly 10-fold difference, which is what's happening at low flows here. But I also don't think that you can completely discount it entirely. So it's a little bit of a thorny issue for estimating sediment loads since the 60s. But for all of you here, I think that the most important takeaway is actually that the best available data we have, which is 7 years of sampling from the USGS starting in 2013, suggests that the sediment loads entering the Duwamish for at least the past 10 years are quite a bit smaller than we previously thought. And then the question moving forward is, how can we use these data to develop a rating curve? Because that's a really important tool for the Duwamish. You need one to estimate sediment input for a hydrodynamic model and to estimate recovery time for the over 50% of the contaminated area that's marked for monitored natural recovery. So I'm going to walk through the rating curve that the Lower Duwamish Waterway Group developed, and then I'm going to show you what I developed, and then I'll compare both of them to the available data. The Lower Duwamish Waterway Group used a combination of two existing rating curves. The first was developed by Harper-O's and was based only on the 1960s data. The Harper-O's fit assumes an exponential relationship between sediment load and river discharge, which means that they have a linear relationship in log space, which is sort of what you see in the plot on the right here, which is showing loads versus river discharge in log space. By visual inspection, you can see that the rating curve does pretty well, and it has an R-squared of 0.8, and R-squared is a measure of how good the fit is, or how closely the rating curve matches the available data. An R-squared of 1 would mean that all of the data points land perfectly on the line and that your model is perfect. Embry and Franz in 2004 used the linear attribution estimate method to develop a rating curve from the 1996 and 1997 data. This method allowed for a quadratic rather than a linear rating curve in log space. So basically, instead of a straight line here, you allow it to curve a little bit. And this means that the rating curve actually fits their low flow and their high flow data pretty well. And they have an R-squared of 0.83, probably because there's still a bit of scatter in that data set. The Lower Duwamish Waterway Group had both the 60s and 90s data to work with, and what they wound up doing was combining the two existing rating curves, using the linear Harper-O's for rating curve for flows below the long-term mean, and then a slightly modified Embry and Franz above the long-term mean flow. And this approach suits the 60s data pretty well, that's the gray data, but generally overestimates the 90s data, which is in blue. And so if you calculate the R squared, it's actually something like 0.63. Now, in practice, it's actually not enough for the fit of a rating curve to look good or have a good R squared value. A good rating curve will predict total annual loads really well. And you can see why that might be a challenge, even for a rating curve with really good fit metrics. Regressions are designed to fit most of the data points as best as they can, but it's not uncommon for most load measurements to be at or below mean flows. And the annual load may be driven by above mean flows or by episodic storm events. So it's really helpful to compare estimates from rating curves to annual suspended sediment load data when it's possible. Now, the 60s and 2010s data both have sufficient resolution so that you can estimate annual loads from them. And those are shown for the 60s in these gray circles and for the 2010s data in these pink circles. So if we use the Lower Duwamish Waterway Group rating curve to estimate annual loads, how does it stack up? The answer is it does really well for that earliest 1960s data, but not so well compared to the 2010s. Seems to overestimate it by a pretty good amount. And this isn't entirely surprising. If you compare the rating curve to all three data sets, we knew it was overestimating the 1990s data, so it's not surprising that it's overestimating the 2010s data. And again, I suspect this is the most useful thing for you all. And it's just a different way of saying what I said before, which is that it looks like there is about half as much sediment coming in as was predicted by the Lower Duwamish Waterway Group rating curve. And it's a tricky problem. How do you use those three data sets, which are sort of telling you different things, to develop a rating curve that matches the available data? The approach that I took was to develop a rating curve for each data set. And I used a method developed by David Jay at Portland State University that allows the slope of the rating curve to change rather than being strictly linear. So this allows the rating curve to fit the low flow data as well as the high flow data. And it's somewhat similar to the approach that Embry and Franz used. The other thing I did was to weight the data, which means that the regression tries harder to match high load data, which turns out to be really helpful in getting the annual load right. And this approach worked out pretty well and resulted in rating curves with R squared values that were greater than 0.97. But like I said before, the test of a rating curve isn't just in the regression metrics. So if we go back to the annual load estimates, the question is, how do we apply those three rating curves that I developed to a time series of flows? The approach that I took was to linearly interpolate the coefficients from 1962 to 1996 to 2013. And that's shown in the purple line, where the shading indicates error bars. And what's nice is that this combined rating curve approach matches the 1960s data really well. And then it also does pretty well against the 2010s data. And if you compare the Lower Duwamish Waterway Group estimates to this combined rating curve approach, it shows that since 1990, the Superfund site, the Lower Duwamish Waterway Group predicted about an average of 1.8 times 10 to the 5 metric tons per year annual sediment being delivered to the estuary, whereas my approach using the three combined rating curves has about half as much, so 0.9 plus or minus 0.4 times 10 to the 5 metric tons per year. And so this all suggests that with less sediment, apparently less sediment coming in than was predicted, the areas marked for monitored natural recovery may be a bit slower to recover than anticipated. With the time series of load estimates, you can also start to understand how and when sediment is being delivered to the estuary. It turns out that very little loading occurs from June to October, which probably surprises nobody, while about 3/4 of the mean annual load is delivered between November and February. And in fact, the mean annual load correlates really nicely with the annual maximum river discharge, which all suggests that most of the annual load for an average year is driven by a relatively few storm events during the winter. So armed with a better understanding of how much and when sediment is delivered to the estuary, Alex and I were really interested in what happens to it inside the estuary. And this is a picture of the estuary. You can see the turning basin and Boeing and a little bit of I-5 in the lower right corner. And this was taken in February of 2012 by Alex, amateur aerial photographer, on his flight back from a conference in Utah. The flows were as high as they get in the post-dam era, nearly 300 cubic meters per second, or a little over 10,000 cubic feet per second. And this was as turbid as we had seen the water in 2 years of sampling. I still happened to be at the conference, but as soon as he landed, Alex sent me this picture and was like, "You should come sample." And I was like, "I should." And so I flew back the next day and coupled together a crew, and I think we managed to get out there the day after. And this turned out to be one of 2 major loading events that we captured, so it was a pretty important piece of our data set. So to try to understand the life cycle of sediment in the estuary, we did a number of hydrographic surveys and mooring deployments between 2011 and 2013. And most of these were during low to medium flows with very little loading, but both the first and the last captured really high flows with significant upstream loading. The hydrographic surveys, basically they capture snapshots of salinity, velocity, and suspended sediment along the center of the channel at different discharges and tidal stages. And then to complement that spatial information, we also used a set of bottom-mounted mooring arrays, which were deployed for about 2 weeks at low flow, low loading, and high flow, medium loading conditions. The spatial transects, or along channel snapshots, basically act as X-rays in that they allow you to see the vertical and horizontal distribution of suspended sediment in the water column. Here's an example from May 2011. Depth is on the y-axis, so the water surface is at the top, and the bed is shown by the dotted line. And this survey extends from the turning basin on the right seaward to the First Avenue Bridge on the left. The shading indicates suspended sediment concentration, and the darker the shading, the higher the concentration. And what you can see here is that there's a decent amount of suspended sediment in the water column, but with a lot of spatial variability. There are these 2 almost tumbleweed looking spots of high suspended sediment concentration, and a place where there is actually lower suspended sediment near the bed, right about here, between the 2 bridges, between river kilometers 5 and 7.5. And this starts to make a little bit more sense when you superimpose the velocity and the salinity. The arrows show strong seaward velocities, and in fact, this data is from a max greater ebb. The thick black lines show salinity, or the salt wedge structure. And you can see that there's actually a lot going on. It's not just this placid slab of salt water. There's a lot of texture, and in fact, at the 16th Avenue Bridge, the flow through the width constriction, which is internally critical for all the fluid mechanics geeks out there, has suppressed the salt wedge locally to the bed, creating a bit of a fold or divot in the salt wedge. This fold and right at the toe of the salt wedge, the landward extent, they're both associated with those 2 locations of elevated suspended sediment concentration. And the low suspended sediment concentration area coincides with the salt wedge. So even in this one snapshot, there's a lot of really interesting information. And if we look a little bit later in the tidal cycle, we can get more information. On the left, that's the snapshot that I just showed you that was at max ebb. And the middle is showing late ebb, so just a little bit later in the same tidal cycle. There's elevated suspended sediment in the area that was recently occupied by the salt wedge. Velocities are a lot smaller, so there's a question here about whether these areas of high suspended sediment concentration are being resuspended or re-entrained. And estuaries commonly have a layer of fluff that's essentially a loose congregation of flocculated particles that can be easily re-entrained up into the water column, which may be what's happening. On the flood, which is all the way on the right here, unfortunately, we weren't able to capture too much of the salt wedge, but what you can see of it shows that there's not very much suspended sediment in the portion that we did manage to capture. So this pattern of suspended sediment at the toe and then being uncovered by the retreating salt wedge in late ebb is really consistent across the range of sampled conditions. So here is a more complete sample of a long channel snapshots of suspended sediment in the estuary. Again, the tide is moving from left to right, and the top two rows are showing really high flow events, high river discharge, and so a lot of sediment coming into the estuary, which you can see because the shading is a lot darker. There's a lot more suspended sediment in the upper water column, especially. During the ebb, you see elevated suspended sediment at the toe and by the bridges, but you also see a transition from sediment being primarily in the upper layer during loading events to being in the salt wedge afterwards in the absence of loading. Late ebb transects tend to show the uncovering of sediment, although the magnitude decreases the further you get from a loading event. And then during the flood, we sometimes see a lot of suspended sediment in the salt wedge, despite a complete lack of upstream loading. And finally, note that this bottom row, which is 200 days after the most recent high flow upstream sediment loading event, there's really no sediment anywhere at all at any stage of the tide. Now, by comparing suspended sediment concentrations in the estuary to suspended sediment concentrations predicted from upstream loading, which comes from the rating curves that I developed, you can get a sense for sediment sourcing. During loading events, the suspended sediment in the upper layer, which is the blue triangles, is comparable to suspended sediment coming in from upstream, which is shown by the gray bars. In the absence of loading, suspended sediment in the estuary is larger than what's coming in from upstream, and it stays that way for a while before it dies down and eventually matches what little is coming in from upstream. And this suggests that some amount of the sediment that is delivered during a storm stays in the estuary for several months after disappearing. And if you rearrange things and plot suspended sediment concentration as a function of time since loading, 3 timescales fall out. The first is sediment delivery, where suspended sediment in the upper layer is really high. There's a lot of it, and it lasts on the order of days, or for however long the storm lasts, that is driving that increase in upstream sediment loading. After that, the amount of sediment that stays in the estuary is primarily in the salt wedge and lasts for about 3 months. And then finally, after about 4 months, the retained sediment is depleted and very little sediment is available in any part of the water column. And so sort of pulling everything together and some bits that I wasn't able to share with you, we've got sort of a basic conceptual model for what the life cycle of sediment in the estuary looks like. So during sediment delivery, this happens during really high flow loading events, primarily during the winter. And there's a lot of sediment being carried in the upper part of the water column. There's a little bit of resuspension happening during the ebb at the toe of the salt wedge. And then all that sediment that's being delivered to the estuary from upstream, some of it settles into the salt wedge, and then some of it is exported into Elliott Bay. And the sediment that falls into the salt wedge, it stays around for like 3 to 4 months and is sort of re-entrained and shuffled around by the salt wedge. There's a little bit of resuspension that happens at the toe during the ebb. But finally, after 4 months, sediment is eventually lost from a combination of seaward export and probably consolidation. And that is probably all of the bits that all of you all are interested in. I just want to quickly thank everybody who helped me and acknowledge that the Duwamish runs through the ancestral lands of the Duwamish Indian tribe, and this work took place on the land and water of the Coast Salish people. We got bits of funding from the UW Royalty Research Fund, Gravity Marine, and Amherst College. I borrowed tons of equipment from a lot of really nice people, and a lot of people generously donated their time to helping me make these measurements. And thanks to my committee and to Alex, who was my advisor throughout the whole process. And with that, I will say thanks and ask if there are any questions.
I'll just make a note as folks get their thoughts together and develop questions. If you could raise your hand, there's a raise hand option under the reactions button that should be at the bottom of the screen for most of you. Then we can kind of take everybody in order. And I think that would be the preferred way. If for some reason you don't want to raise your hand and ask your question yourself, you can put it in the chat and we can read it out for you. Rachel.
This is Ellie, and I'm not even seeing where you raise your hand, so that's why there's this long pause. Maybe somebody else is having the same problem. Where is the hand raiser thing?
Okay, let's see. Why don't we take down the slideshow? If you could stop.
Oh, there it is. Okay.
Yes, certainly.
No, don't take it down.
I know some people have different setups, but on most screens, you should see in the bar at the bottom a reactions button. And if you click on that, you should be able to select raise hand. If that doesn't work, you can also do it on the participant list at the side in association with your name. And if that doesn't work,
or at the bottom.
Yeah, if that doesn't work, put it in the chat and we'll take care of it for you. So I think we had Rachel and then Ellie.
Good afternoon, everyone. Rachel McCray, Department of Ecology. I just want to ask a clarifying question around you said the high loading events, falling into this November through February time period. Based on previous conversations and presentations we've had from the operators of the Howard Hanson Dam and the dam releases, it's my understanding that those tend to be the highest, also correlating to the higher load events. So I'm curious if you looked at that dam operations piece, and maybe didn't just mention it today, but I'm just curious about that.
I didn't look specifically at how many high loading events were correlated with dam releases.
Okay.
For the ones that we sampled, you could absolutely see the flows being modulated. It's hard to tell on the big time series that I showed, but you could see it looked like a little step pyramid. So anecdotally, at least one of the ones that I sampled was related to dam release, but
Okay.
I haven't correlated them entirely throughout since 1962.
Yeah, no, that's okay. I just recall that sometimes they release the dam in advance of a storm event. Sometimes it's during, so there's a little different timing around some of those dam releases. Thanks.
If I can jump in and add quickly to that, just to acknowledge that we did get some support from colleagues at the Army Corps in planning some of these field campaigns. And so we would get a heads up from them when they anticipated that they would be doing a release. So that some of our field campaign surveys, especially when we were trying to capture the high flows, were benefited from that information and therefore definitely corresponded to planned high release events.
Thank you.
Okay, and Ellie, and please go ahead and everybody can actually turn on their video if they want now, but if you're going to ask a question, go ahead and turn on your video as well. And Ellie, I think you're up.
Okay, there was a little lag time for my picture to show up. And now I'm trying to think, what was the question I was going to ask? And I think it's the turning basin itself. So you've got all this information about what comes into the waterway. And then you have samples, which I think you were taking along the course of the waterway. Did you have actual measurements in the waterway section south of the north of the turning basin?
Sometimes, if the river flow was really low, then we were up above the turning basin for sure. I think as far as for kilometer 14 is probably where we went, and then it got quite shallow.
Yes. Well, I guess what I'm trying to figure out is how much the sort of what might be interpolation accounts for stuff dropping out at the turning basin.
Mm-hmm. I think that a lot of the material that falls into the salt wedge happens in that area near the turning basin. I didn't show this, but I calculated removal rates from the upper layer, the part that was carrying the sediment from upstream, and calculated how much of it was falling into the salt wedge, estimated from the transects, the snapshots that I showed. And those calculations indicated that most of the material that drops out of the upper layer drops out within like a kilometer and a half of the turning basin.
Okay, I think I get that. Sounds good.
Tom?
Hi there. Just a question to follow up on the turning basin question. Did you, when you looked at it too, I mean, the river widens obviously from upstream of the turning basin to a lot larger wetted perimeter. And that often has, effect of why sedimentation occurs at a much higher rate when the river widens. Was there any attempt to kind of try to also look at that correlation? I mean, I understand the salt wedge things and whether it's coincidental or not, it's around the same location, but also look at it purely from the physical dynamic standpoint of current velocities just upstream versus in the turning basins versus downstream. Was that, I'm curious to see what correlation was looked at.
Yeah, I mean, that's definitely, I mean, that's why the turning basin is there. It's to promote sediment dropping out, regardless of what the salt wedge is doing. But because the turning basin is there and because that area tends to be dredged and deepened every 2 years or so, the salt wedge actually likes to hang out there quite a bit because of that change in depth and change in width. So, I mean, both of those factors are at play, but it's a little bit hard to disentangle because the salt wedge really likes to be there.
And then I had one other question. So the 2013 to 2020 period, it sounded like the information was using turbidity, but correlated back to suspended solids. How did
suspended sediment specifically, not just suspended solids, I believe.
Right,
Although I think that Craig Center, who actually his 2018 paper goes into that data and was involved in collecting it, is actually here. So if I'm getting any of this wrong, jump in.
And I'm just kind of curious about the variability because I know the relationship between turbidity and suspended solid concentrations can be quite a large range depending on different factors. I'm just kind of curious how tightly correlated that relationship was for that data set.
It was very well correlated, like over 0.9 R squared. It was really tight and it looked really nice. Okay. They also tried to correlate, I think, suspended sediment with river discharge, and that had a lot more variability. But in terms of correlating the turbidity and developing a calibration relationship with suspended sediment, that relationship was really strong.
Great, thank you.
Mm-hmm.
Okay, I think Earl Hader has a question. Are you able to speak up and ask that, or did you want to type it in the chat?
And yes, I'll ask a question. My laptop does not have a camera, but good presentation, Maggie. I was wondering, did you have grain size distribution data for the suspended sediment as a function of space and time?
No, we did. A master's student who was out there with me on a couple of these, he was working on trying to get list data to make sense. And list data essentially does suspended concentration. You all probably know this, but for anybody who might not, a list will give you suspended sediment concentrations for particular grain sizes. But it's really tricky to use a list in a stratified environment like the Duwamish, because it can misinterpret changes in water density. So as you move from the freshwater down into the salt wedge, it can misinterpret those changes in density as changes in suspended sediment concentration. And we were never really able to get that data to work out. So the only grain size data I had that I'm not showing here is the percent fines data that the USGS collected at the Tukwila station. that gave how much of the incoming data was fine sediment, and I think a few other classes as well.
Okay, thank you.
Ellie.
I am remembering that when you sent the invitation out, BJ, you sent some kind of an abstract, and it seemed like it suggested some other information, some other conclusions. And now I'm not remembering what those were, but Maggie, I assume you've seen your summary, your abstract. It seemed like it was a kind of about circulating or something. Am I remembering something wrong? Or is there another piece of this topic that you didn't cover?
There's a few things that I didn't quite get to, which was looking at bed stress measurements, and then getting really into the nitty-gritty of the hydrodynamics that govern the salt wedge structure. And those are all available in my PhD dissertation, which I'm pretty sure that if you Google my name and UW dissertation, you can get there. And then the hydrodynamics portion has been published in 2020 in Estuaries and Coasts. So that's available also as a peer-reviewed publication. The other bits of my dissertation, I'm currently still preparing those manuscripts for review.
Thank you.
Mm-hmm.
Looks like Craig has put it in the chat. That's nice.
Great, thank you. Other questions? Comments?
If there are no other immediate questions, I will just sort of add on to that and say that one of the big takeaways from the hydrodynamics portion is that the width constrictions at the 16th Avenue Bridge and the First Avenue bridges have really big effects on the salt wedge structure, and they seem to be linked to suspended sediment. I haven't fully been able, my measurements aren't totally capable of elucidating the full impact of the bridges on suspended sediment transport, but I think those are really important areas of the estuary to look at as well, especially during large tides and high river flow events.
Yeah, and I'd add a little bit to that, just that one of the interesting things that people often ask us about this is to what extent sediment's actually transported back up the river within the estuary. And we certainly see that on flood tide, that the transport is landward. But the hydrodynamics that Maggie's referring to look like they may actually cut that off. And so these constrictions at the bridges may force the transport and circulation to be kind of segmented a little bit between the bridges to an extent, like Maggie's saying, that we can't really evaluate fully with the data that we have, but there's some sense that it may be hard for sediment to pass back upstream under some conditions past those bridges.
Can I ask another question? So I think I saw your maps were pretty much for the size of the Lower Duwamish Waterway, but there's also East Waterway and West Waterway on either side of Harbor Island. Did your modeling or consideration go beyond Lower Duwamish?
No, it didn't, because, well, first of all, I was in a very tiny boat and there are some very big boats down there. And secondly, more importantly, really, the impact of the salt wedge on suspended sediment transport is mostly important at the toe, at the landward extent, where you have fresh water with really high bed stresses then meeting that intense vertical stratification. The salt wedge is always present from the First Avenue Bridge all the way to Elliott Bay, because the channel has been straightened and kept really deep. So the salt wedge is never completely flushed out. And so I really focused on the portion between the First Avenue Bridge and a few kilometers above the turning basin, because that was the area where we thought that the effect of the salt wedge hydrodynamics was going to be most important for understanding suspended sediment transport.
So that phenomenon of the suspended sediments that are carried down in the fresh water, but then sort of drop into the salt wedge, would that mostly be occurring in that same zone that you were focused on, or would that also happen elsewhere?
I think that it happens to some degree throughout the entire section that is occupied by the salt wedge, but I think it happens most intensely right by the toe of the salt wedge, about a kilometer and a half seaward of the toe of the salt wedge, which tends to be close to the turning basin.
Thanks. Anybody else have questions from the core, for example? It was a great presentation, Maggie. Thank you.
I'll add a question. This seems obvious, but I'm not sure it is. How closely tied is the difference in sedimentation rates that you found, or sedimentation load that you found, to the time expected for natural recovery?
I haven't estimated sedimentation rates from the upstream loading estimates that I have done. And so what I've found is that it seems like there's roughly half of the amount of sediment coming in than was anticipated. And so back of the envelope, I would expect maybe it would take twice as long to recover. But I haven't done any extensive calculations or estimates to really make that more than a back of an envelope. Very rough estimation.
Okay, thank you.
Yeah, I'll add that I guess these conclusions leave open kind of two questions, and one is of the sediment that comes in from upstream, what is trapped, as it passes through with the freshwater layer? What ultimate sediment ultimately ends up in the estuary, which is probably a pretty big fraction. How much ends up in that kind of upper part of the waterway versus down by Harbor Island? Maybe a harder one, but we can make some estimates. And actually, Maggie has done that for her transect work. So there's sort of anecdotal snapshots of how much sediment is being removed just as it's initially carried over the salt wedge. And then the second one is, of the sediment that's removed, where is it ending up? Is it over the next 3 months during this sort of that second time scale Maggie described? Is that ultimately being sort of reprocessed and spat back out of the estuary? Or are we losing it from the estuary because it's forming part of a consolidated part of the bed? And some of the work that Maggie didn't present shows that there are times when you get high bed stresses and you don't, usually if the bed stress goes up, the sediment concentration goes up. And that shows that there's sufficient source of sediment on the bed. And what happens points later is that you can get high bed stresses, but you don't see sediment being resuspended. And so that either means that the sediment's being lost from the system, or that it's consolidated enough into the bed that it's more permanent there. And our measurements can't differentiate between those two outcomes. And so those are sort of two outlying questions, both what is the flux out of the system, which we didn't measure, and what is, how do we figure out the incorporation rate into the bed?
Super, thank you. We do have a couple more questions. Bo?
Yeah, so I want to follow up on the sedimentation rate, because I think it's a very key assumption. In our early discussion, I think a couple of years back, when we had this type of information about estimates about half the load coming out from the upstream compared to what originally assumed in the log weight sedimentation model. I remember the discussion, I think at least at that time, I think the conclusion is because the sedimentation rate didn't change. And so basically saying like there are so much sediments coming out from the upstream. And so if the sedimentation rate didn't change, so it's actually the modeling result won't change because for example, for our POA, for pooling loading assessment model, our ecology is developing right now. I think the key parameter is looking at what the sedimentation rate it is. So I'm not saying what my conclusion it is. I'm just want to bring here. I just want to mention this to remind everyone. I think remember there are a lot of discussion around this. I think that will be a key factor we need to look into more to evaluate what the sedimentation rate, because it's actually different from what the loading it is. And because it actually could change the equation quite a bit. I just want to throw it out here, and I would love to open that discussion to anyone have more opinion or suggestion on this topic.
Maggie, did you want to, or Alex, did you want to respond to that at all?
I'm interested in Maggie. Did you have something?
No, go ahead.
Oh, I guess I'm curious how, if you have the loading rate, you'd have to double the sedimentation rate to get the same, net. And it's possible that we're using sedimentation rate differently here. So when I'm saying sedimentation rate, I'm saying the rate that sediment that has come in is falling out and being deposited in the estuary. I don't know what mechanism would increase that other than a shift in particle size. What mechanism would increase that relative to, the upstream loading? So I guess I'm interested to hear how you'd get the sedimentation rate staying the same if the loading, or the rate of sediment being deposited, let's call it that, staying the same if the loading was going down. Does someone know how that was being explained?
I could take a layman's attempt at answering that. If any of you have kind of reviewed the sediment transport modeling that was done by the Lower Duwamish Waterway Group for the feasibility study, the particle size distribution in the incoming sediment load was used as a calibration parameter to estimate actual sedimentation rates. And the calibration was to geochronology cores. So actual evidence in the sediment bed of the sedimentation rate was used, and then the particle size was used as a calibration parameter because there's uncertainty on that particle size, right? To kind of force the sedimentation rate to match geochron cores. And so, and then we adjusted when about 4 or 5 years ago, there was, I don't know if it was this same body of work or a separate study that was calling into question the sediment, the total annual load. We actually wrote a memo that, if this newer load estimate were, taken as the correct one, you would adjust the particle size in such a way that you still can match and calibrate to the actual measured sedimentation rates from the geochron cores.
And the sedimentation rate from those geochronology cores, is that the long-term sedimentation rate? Would it capture a change in sedimentation rate from like the last few decades?
That would, I can't answer that off the top of my head, in terms of the time. It was longer term timescales in general. Whether it would capture, say, a 2-decade, I'm not sure.
We did 2 different geochron cores. One is short term and one is longer term. So those rates were both looked at. And the shorter term really doesn't capture more than about a decade or so of sedimentation.
And Jeff, is there any suggestion between comparing those two that if things are pointing to the loading decreasing, but those two both suggest that the net sedimentation is the same, something else must be happening. Is there any, do they show the same sedimentation rate? And if so, how do people make that make sense with the potential of changing loads?
Yeah, Bruce, you can jump in here too if you have a better memory than I do on this. But the variance on these measurements jump around quite a bit, right? So I seem to remember that there was no distinct pattern of the one measurement being always, lower or higher than the other measurement. I thought they kind of jumped back and forth a little bit. But Bruce, do you know if the cesium rates were in general a little lower than the lead rates?
No, I don't remember.
Yeah, either do I. It's a good question though.
I'm sorry, can somebody explain the question again? Because I'm not tracking.
I can take a stab at it. The question is, Lower Duwamish group used geochron cores to estimate the actual sedimentation rate within the Lower Duwamish waterway, and with the evidence or suggestion that the incoming load to the waterway is decreasing over time, was there any evidence from those geochron cores that we're seeing lower deposition rates currently than we have historically? And I don't recall any particular evidence of that. I also don't recall that we specifically attempted to look at differences, in the current decade's sedimentation rate relative to historic. And obviously, when you look at load, that it's also highly dependent on what the flows were in the past decade, because as Maggie showed, it's, the loading is really dominated by those large storm events.
Okay,
That would be interesting to go back from those, the timing of the geochron cores, and for if it's cesium, I don't know what the time window is, but you can assume that you're capturing changes over whatever 1 or 2 decades, and sort of go back and integrate that and see, you could look then in these revised rating curves and make estimates of what you would predict in terms of net loading, and make that more direct comparison.
So we're coming up on 2 o'clock, and I want to be respectful of folks' time. Maggie, did you have any last remarks you wanted to make?
No, it was great to have the opportunity to share this with you all. I hope it's useful. Please contact me and Alex if you have any questions.
Could you both put your contact info in the chat for folks?
Yes.
Great, thank you very much. I'll give everybody a moment to capture that if you wanted to be able to follow up with them. You're also welcome to email myself or Tom or Lisa. And thank you all for taking the time to be here today. Appreciate it. Maggie, thanks so much.
Yeah, thank you. Thank you all.
Thanks a ton.
Thank you.
Thank you, Maggie.
Thanks for setting this up too, BJ. Appreciate that.
Ditto. Thank you for spreading the word. Let's see. Joe and Pete, are you still there? Let's see.
Maggie, that was an awesome presentation.
Oh, thanks.
You explained it very well. It does seem really tempting to try and compare the cores.
Yeah. I remember when I looked at the core data that it was kind of all over the place.
Yeah.
It was very hard to, even for the long term, to draw a conclusion about sort of what was happening. So I wonder if it makes more sense to try to capture a storm event and put some sediment traps down, which I think would be really tricky given how soft the sediment is, but it might give a better idea of like what the short-term sedimentation rates are.